This is the second part of taking a look at example questions on the topic of pH and logarithms. This section, titled Extreme Dissociation, is also found on Chem and Rich, and as the title does suggest, we are going to be taking a look at the hypothetical limits of the equation pH equals negative log to the base 10 of the concentration of H plus ions. And a few things to mention in this notes and background section, as you do see at the bottom, as we consider pH to be typically rated on a scale of 1 to 14. However, this is not the case. In the case of many acids, such as superacids, as the footer does state, pH can actually drop below 1 or even go into negative values. And for extremely alkaline solutions, as you can guess, with an extremely low concentration of H plus ions, it can actually exceed 14 empirically. Another thing to mention is that for weak acids, when they dissolve in water, often they do not directly correlate and perfectly fit this equation that we have been using so far to such a good extent. This is often the case because water, not all water, will dissociate. We know that water typically undergoes the reversible reaction where it splits into a positive hydrogen ion and a negative hydroxide ion. However, for weak acids, this is often not the case, and for many acids themselves, acids split into a single positive H plus ion and whatever their other conjugate alkaline ion is. And the way in which they actually split, and the ratio by which these two split relative to the starting acid or water, is called the dissociation constant. And it's very important when we're trying to make calculations, trying to work out the pH of a solution. I'll probably cover it in a future video. Okay, so now going on to the first question. We are going to be starting with what we have been starting with before. We are going to write this very important equation, as you will see. You will see how important it is sooner. We have pH equals negative log to the base 10 of the concentration of H plus ions. Now, one thing very important to notice and to take note of in this section of questions is that concentration is defined as moles per liter. Liter is often known as a cubic decimeter, or dm cubed, more simply put. This is very important, and we're going to try to remember this when attempting all these questions. So, imagine that this equation works for any concentration of H+, important because of what I previously mentioned, and imagine that scientists have created conditions in a 100 milliliter sample of pure water in which only one molecule has associated into H+ and OH. Such conditions are, of course, science fiction. What would the pH of this fluid be? Well, right off the bat, we can see that because only one molecule of water has associated, we can see that this is an extremely alkaline solution, and we are trying to find pH. So let's see what they have given us so far. Right off the bat, we can see that they want us to find pH, so this is very important. We're going to be incorporating this equation from the start. So this whole equation is empirically set on the concentration of H plus ions. We see a negative log 10 pH. These are all dependent factors on this one concentration. So that's why it's very important to remember its constituent properties, how many moles of H plus ions there are, and its volume given in liters. So we know that one molecule has associated, and there are 100 milliliters. So we can say that volume equals 100 milliliters, which is the same as saying 0.1 liters. So there, we have something right there to get us started off. Now we want to find the amount of moles. Now, how do we do that? We know a mole is given by Avogadro's constant. It's just any number, but it's given through Avogadro's constant, 6.02 times 10 to the power 23. This is given as 1 mole of something. So if we know that one molecule of water has associated, that means that one H plus ion will be formed. So we know one ion will be formed, and we want to find it in moles. So we do 1 over what is given as a mole. There we go. Now, next we want to find its concentration. That's what we're basing this whole thing off of. So if we take a different color, therefore, the concentration of hydrogen positive hydrogen ions will be given as the amount of moles, 1 over 6.02 times 10 to the power 23, divided by its volume, is given as 0.1. Now, if we rearrange this, we can move this to the top. Therefore, we know this is the same as saying 10 over 6.02 times 10 to the power 23. Now, using indices rules, we can change this to 1 over 6.02 times 10 to the power 22. Now, this is our concentration of hydrogen ions. Now, we just substitute this back into the starter equation. Therefore, the pH of the solution will be equal to negative log to the base 10 of our concentration of hydrogen ions, which is 1 over 6.02 times 10 to the power 22. Okay, let's plug that into the calculator and see what we get. We should get this, approximately 22.8. So 3 significant figures as our pH. As we already see, this is way above our typical maximum of 14. Okay, let's go on to our second question now. Okay, let's get a new color. Let's start by writing our equation again. pH equals negative log to the base 10 of the concentration of H plus ions. Next, imagine that conditions arise in which every single molecule of water dissociates. What would the pH be now? What assumptions do you have to make in the calculation? See, to me right there, what assumptions do you have to make poses quite a big hint as to what we have to do to solve this. Once again, it's asking us to try to find what its pH will be, but instead of one hydrogen ion dissociating, all water molecules dissociate into hydrogen and hydroxide ions. So let's try to do this. We remember again that we just want to keep these as they are because we can't really vary them. So we're trying to find the concentration of hydrogen ions. This is given once more in moles per liter. So what do we know about its volume? We know that its volume, we know that this is a lead-on question, so its volume remains at 100 milliliters. We know that 100 milliliters is the same as saying 0.1 liters, so we have that already. Next, we try to find the amount of moles. Now, this is a tricky bit. What do we know about moles? We know that the number of moles are given by mass, given in grams, over our substance's molecular weight. Now, how do we get these values? Well, we know that every single molecule of water dissociates. So through that, we know that we're looking at water. Now, let's try to work out our molecular mass. We know that water consists of hydrogen and oxygen, H2O. We know that hydrogen has MR of approximately 1, and we know that oxygen has an MR of approximately 16. Now, combining these together gives water an MR of approximately 18. So there we go. We can substitute this right in, which equals to our mass, which we are trying to find, over 18. Now, how do we find our mass? There's no mass given here, but all we do know is that there are 100 milliliters of this solution. Now, one very important thing about water is that it has a density of water, the density of approximately 1 gram per milliliter. Now, this actual value is nearer to 0.997 grams per milliliter, but here we'll just keep it as 1, and I think that's the assumption they want us to make. So if it does have a density of 1 gram per milliliter, we can then assume that 100 milliliters will be approximately the same as saying 100 grams. So therefore, the amount of moles that we have of water in this solution will be equal to 100 over 18, our MR. Okay, so we have that now. So we go back to our original equation, and we're trying to find the concentration of H plus ions, and we know the moles, and we know the volume. So let's try to work it out. We have moles over volume, which is the same as saying 100 over 18, all over 0.1, once again, which is the same as saying 1,000 over 18. Now we substitute this back into our original equation. Therefore, the pH of this solution will be the same as saying negative log to the base 10 of 1,000 over 18. Now let's try to plug this into a calculator and see what we get. Now this gives us approximately a pH of 1.74 to three significant negative 1.74 to three significant figures. Very acidic indeed. Okay. Now we'll go on to our final question. Next, okay, under real-world situations, what volume of water would we expect to contain exactly one hydrogen ion? Now, once again, we start off by writing pH as being negative log to the base 10 of our concentration of positive hydrogen ions. What volume of water would we expect to contain exactly one hydrogen ion? So, using the information they have given us, we know that we're trying to find a volume of water. What do we know about water? We know pure water has a pH of 7. Now, if we just substitute this in, 7 equals negative log to the base 10 of the concentration of hydrogen ions. Now we know from our previous video that we can rearrange this quite orderly to know that the concentration of hydrogen ions in pure water is the same as 10 to the power negative 7 moles, because this is concentration in moles per liter. Now, what volume of water would we expect to contain exactly one hydrogen ion? Now we know that it contains 10 to the power negative 7 moles of it. Moles is just another unit. It's like what a meter is to a kilometer, but it's given by the very weird value of 6.02 times 10 to the power 23. Avogadro's constant. Now we want to try to find one. We want to find what one hydrogen ion would be in moles. So we can do that. We can do that through taking one hydrogen ion and dividing it by the number of moles. But we want to maintain the concentration to find what volume we would get. So we get 1 over 6.02 times 10 to the power 23 multiplied by our concentration multiplied by 10 to the power negative 7. Now we can actually do this right away to find the volume that we need to find in liters. And the reason that we're doing this is we're taking ratios essentially. So we're taking the ratio of one positive hydrogen ion to the amount of hydrogen ions present per liter as a ratio to volume in liters that we're trying to find per liter, in which would be the denominator in this case. And we know that it's per liter, per 1 liter, so we can say that its volume is the same as 1, and anything over 1 is the same as itself, so we can cancel this out. So now let's try to write this out. So if we plug this value into a calculator, we get a volume of approximately 1.66 times 10 to the power negative 17 liters, which is the same as saying 1.66 times 10 to the power negative 14 milliliters to three significant figures. Now this is our answer. A very small, extremely small amount of water to us would only contain one H+ ion.